Hello, my name is Matthew Landis, and this is my Lab 5 presentation. This lab is concerned with Faraday's law with time-varying magnetic fields. It includes both real-world experiment and a digital simulation of similar scenarios. The goal of the lab is to compare real-world simulated scenarios, which can provide us with a deeper understanding of how time-dependent magnetic fields relate to electric fields and induced currents. On the top left, you'll see the formula for a magnetic field, where the magnetic flux is equal to the magnetic field times the area perpendicular to the magnetic field B. To the right, you'll see Faraday's law of induction, where we're able to take the induced current, or the EMF, is equal to negative N times D times the flux over dt, which can then be written to the formula on the right that is used in the lab for our calculation of the EMF. Also to the bottom left, you will see the same formula that was used in lab 3, where we're able to solve for the magnetic field based off of the magnetic moment and some other values, and then just the simple formula V equals Ri is used multiple times in this lab. In the experimental portion of the lab, I began by testing what would occur when you drop a magnet down a roll of aluminum. Unsurprisingly, the magnet fell through. The unusual part came when the time it takes for the magnet to fall the distance of the tube. When comparing the time taken for the magnet to fall the distance of the coil, when inside versus out, it is very apparent that the magnet takes much more time when falling inside of the coil. This, as explored by the rest of the lab, is related to the changing magnetic field, but creating an electric field, which induces a current in the conductor surrounding it. The induction of the current takes energy away from the magnet, which will in turn slow the magnet down from the reduction of the kinetic energy, which is associated with a force which opposes the direction of motion. It is important that we choose the material that we're dropping through the magnet properly for this phenomenon to occur. If we picked aluminum foil, use it as a conductor, and thus we'll have a current induced through. However, we picked something non-ferrous, unlike steel, which would have had a magnetic attraction to the magnet, and thus would have acted as another force to consider. On the screen now, you can see the code. The most relevant parts are on line 98, where you see the formula taken for lab 3, and then on 115, where there's the formula that is now used to solve for the flux. This code is linked both on screen now and should be linked in the description. The goal of this simulation was to digitally represent the situation and the physics that we were observing in our real-world experiment. I began my modification of the code with the inclusion of the code written for lab 3 to calculate the magnetic field of the magnet on each of the rings making up the rod. It then allows us to use the magnetic field to calculate the flux of the rod and by extension the force of the magnet. This is the force earlier referenced, which opposes the direction of motion, decreasing the acceleration that is experienced by the magnet while it descends. Just like in the real world, if you remove the coil, then you'll see the linear slope of a velocity curve simply with the slope of negative 9.8. However, when you compare the graph that is seen with the experiment on screen now, you can see that the velocity curve initially has a very high slope, but pretty quickly levels off. This initial slope to the velocity curve should be about negative 9.8, which is expected as the coil has a very small velocity, meaning the flux and therefore the induced current are both very small. However, as the velocity begins to increase, the magnitude of the velocity begins to increase, the induced force balances out with the magnetic force, and thus leaving just the net force of about 0, keeping the velocity constant. This bringing the change in velocity to 0 is what causes the increased time for the magnet to fall as it stops speeding up as partway through its descent. With the code, we assume that there was no air resistance or non-conservational forces of any kind. Also, you can see at the bottom where it says that it took approximately 2.1 seconds for the simulated magnet to fall through the tube. This is very comparable to my experimental value of an average of 2.31 seconds. This difference is likely the result of my foil not being exactly the recommended thickness of 1 centimeter. So, what if the resistivity of the conductor were reduced to 0, or as close to 0 as possible? If the resistivity of the conducting tube were extremely low, then we would find that the magnet would generate a much greater current in the tube because the EMF, or the deflux over dt, would remain the same, but the reduced resistance would create a far more significant current. The massive current would be applying a stronger force on the magnet, thus bringing the acceleration to 0 even quicker. What if there were holes or slots cut into the tube? How would this affect the ring of currents in your model? If there were holes in the tube, like seen on now, like seen on screen now. This would simply reduce the amount of conductive material, thus reducing the magnetic field that is being induced, which means the current would be lower, and thus we would see the magnet falling faster than it otherwise would have. Thanks.